slipping is going to involve Coulomb friction, which we'll get to in a moment here. So we're only dealing with static friction, not kinetic friction in this course. The static friction is always going to oppose our impending motion. So again, when we're in static equilibrium, we are not actually going to be accelerating to the right or left or up or down. But what we want to think about is, if it were going to accelerate under these conditions, would it want to move to the right? If it would want to move to the right if the friction were not there, then the friction would be pointing to the left. The friction force will always impose the impending relative motion. The friction always opposes the direction of motion or impending motion, but the friction itself cannot cause the motion. Basically, a friction force is going to be as large as it needs to prevent acceleration from happening, but there is an upper limit as to what that maximum friction force can be that prevents motion from occurring or prevents accelerations from occurring. The friction force, Fr, can be less than or equal to mu times n, where mu is going to be the coefficient of static friction between the contacting surfaces, and n is the normal force or the contact force between those two surfaces. So this is true that it's less than or equal to mu times n when we are talking about Coulomb or dry friction, that the friction force has this upper limit. When we are just on the verge of slipping, that if we applied any more force it would start to accelerate, the friction force is then at its maximum possible value, and the friction force would be equal to mu times n. The important point here is it is not always true that the static friction force is equal to mu times n. It can be as large as mu times n. And we want to keep in mind static friction cannot cause an object to move. It can only prevent motion. Now, when thinking about kinetic friction in a dynamics setting, we have a very similar equation there, where the force of dynamic friction is always equal to mu times n in that case. But in a dynamic case, the mu is different. That's the coefficient of kinetic friction. And yes, when we are moving, in that case, our force of friction is constant. But for static friction, it is not. It is capped at mu times n. So what we want to do is we can test if an object would be slipping. We always want to be assuming that we are in equilibrium and then either disproving it and showing that the system cannot be in static equilibrium under a set of circumstances, or what would it take to be on the verge of slipping. So if we are assuming static equilibrium, we can solve a problem and we can solve what the static force of friction would be in order to keep our system in static equilibrium. We can solve for Fr. And in a case where we're testing, is this system in equilibrium or not, we can then compare that Fr to the mu n. Again, this is only for a pair of surfaces, is the Fr, the mu between them, and the contact force n between them. If to maintain static equilibrium, the force of friction would have to be larger than the mu times n between the surfaces, our system cannot be in static equilibrium, because to maintain static equilibrium would require a larger friction force, static friction force, than is allowable. If we go through our equations and we find the force of friction is below mu times n, then the system is in static equilibrium and it would not be accelerating. Now, sometimes it's not necessarily clear what direction a system wants to move in, so the direction of impending motion may not be obvious. Therefore, if we don't know the direction of the impending motion, we won't know the direction that the friction force should point. So if it's unclear, we want to draw it in a direction we think is right, but when we go through the mathematics, if we find our friction force is negative, we actually do want to redraw our system, because this is a case where the math won't just work itself out because of the additional friction equations that we are imposing. If we encounter a negative friction force in our answer, we actually want to go to our free body diagram, draw the friction force in the opposite direction, rewrite our equations, and then solve it that way. Now, prior to this, without friction, it was not a big deal if we got a negative value for something. As long as we used everything consistently, the negative just told us our assumption was wrong, but everything else worked out. In friction problems, that is not going to be the case because of the relationship between the friction force and the normal force. A wrong direction can throw off the entire problem. Also, a normal force must be positive. If we come out our answer as a negative normal force, we also want to redraw that because a normal force can only push, it can't pull. So if in our solution we're finding that a normal force is negative, a surface would be pulling on another surface, and that's not going to be possible.